that this is something important that you'll learn in the introductionary, or especially like maybe the derivative chapter, like I think it's unit 2 of college board when you get into that. So you still need to know this, especially if you want. This is useful for getting into more details of why we get a certain thing for derivatives, why does it happen. So there are two methods to using algebra. So mainly algebra. So of course I know first example it's using limits, a calculus topic, but mainly it's algebra here. So either we have the similar function or the similar definition of derivative, but the a is telling us that, oh, we have chosen a specific point. So the definition or formula I just showed you originally, that was to look at the derivative of a given function overall, okay? Overall, because maybe we can use that new function, and that new function can tell us, okay, tell us at this point, just plug in the value. Now at that point, plug in the value, and so on. Now, besides that, as I said, for second method, um, as I told you, instant rate of change. Rate of change is slope. This is something you should remember from Algebra 1. Okay, so basically, for this, as I said, don't just say that, hey, what's the derivative at x is equal to 4? And you tell me that you use the points x is equal to 3 and 5. No, do not use that unless if there is a like a urgent situation that, okay, I might use 3 and 5 because maybe, oh, I'm just given with the table, so I'm not given a lot to work with, then okay, that's fine. But overall, if you're given with everything like the graph or the function, then you should try to find the closest points. As I said with the limits, which limits are part of the definition of derivative, as I said for limits, we are getting so close at a specific point. If it's not infinity, we are getting so close at a specific point. So like that, if that's part of the definition of derivatives, same thing. You need to get so close to the given point, right? It's instant rate of change, right? If your boss get angry at you, you need to start getting back to work. So like that, that's basically when the question asks you, you need to find the instantaneous rate of change or derivative. You need to find at the closest area. How fast is it changing, right? If the police pulls you over for speeding, do you know how fast you're going? Right? You're going over the speed limit at a specific point, right? How fast were you going in a 30 mile per hour zone? So like that, you need to use two points close to each other. So x is equal to 4, let's say, for a given function. Find derivative of that at that specific point. So some, for example, x is equal to 4.01 and 4 x is equal to 3.99. Okay, these are two points close to x is equal to 4. Let's make it more specific. 4.001 and 3.999, we can get keeping like getting closer to each other, right? So that's basically what's happening here. So just we are, I know I say method 1 and method 2, but just keep in mind the first method is this one, the second method is this one. So first method, the one that looks similar to the regular definition. So let's say we are given with this, and f of x, f of x is 4x squared minus 5x plus 3. And I told you find the derivative at x is equal to 3. So what is the instantaneous rate of change at x is equal to 3? That's the question I am asking you right now. Um, so basically, um, first thing we need to know what's f of a. So basically, right here we are given with like a binomial format with a plus h, and we are given with f of a. So right here the 3 plus, since we know a is 3, we need to input 3 plus h in these function this wherever there's x, and then we also need to put in 3 for a in the corresponding places for f of a. You simplify it. So just to help you out, guys, this is basically what it is. You do cancellation and so on, and there minus 24, and then you do this, and then so on. Or I think the cancellation will be best understood for normal definition, because this is now we're looking at specific point. Then we do everything and so on to where we simplify. So um, right here for h square is for h, then 30 it still remains over here, but 19 is by itself, so everything comes to 0. I know this part looks confusing of 30 over h. Oh, we cannot divide by 0, but think about back to that area of the infinite discontinuity example, right? So maybe you can associate it to that's why this is allowed of limit h approaches 0 of 30 over h. So therefore we get everything out, we are left with 19, and that is the final answer. Same thing if I told you using the slope formula, okay? Right, as I said, we need to try being so close. Okay, sorry if I keep emphasizing strongly on that, but to get the point across, you need to understand that this is what the derivative is about. This is why the derivative happens, especially when we work at specific points. So I apologize for my being over stressing so much on this, but for you to understand derivatives, you need to understand this thing of instant rate of change, of why it happens, right? Um, right, when you're learning, maybe if you're taking it as college course, your calculus 1, or maybe AP calculus AB in the high school, then you should know why it happens, right? So we use, as I said, the two close points is 3.001 and 2.999. Of course we can get more specific to that, saying like maybe 3.000000001 and then maybe 2.9999 and so on. But of course this is like simple example. Of course we cannot go to that extent as like humans, but this is, as I said, a good reference. So we plug in the values, we get this, and we have this x values. We simplify, we get 19. So same thing. And by the way, the function that I used was same exact thing. They were both same questions, but it's just I asked you what was, how do you do it in method one and how do you do it in method two. So this is sort of over for the algebra part of finding derivatives. Now we are gonna get a little bit more serious with actually looking at the more calculus part of derivatives. So just to get an understanding, can anyone, if anyone has any question, please put the question below or say yes or yes I understand, so I get an understanding of who needs clarification. Does anyone have any questions? Okay. I believe since no one else is asking any questions, I only see one I understand. I'll move on. You can all guys feel comfortable to ask questions on the way. I can always look back when I check back Discord. Um, so now there's few rules. Given these two rules I told you in algebra, the more calculus part that maybe, as I said, like if you're taking an AP Calc AB exam, or maybe you're taking a final exam for Calc 1 in college and it's timed, then instead of using these algebraic methods, what's the faster way to do it? So there's power rule, product rule, quotient rule, chain rule, implicit differentiation. So I would say in these order, I feel like these are coming from easiest to hardest, the power rule being easiest to implicit differentiation being hardest. And as you can see for when I am talking about the power rule, there for the power rule there is some complications that you, like there will be certain situations, like if I told you just use the algebra method for sine of x, cosine of x, ln of x, that might be somewhat confusing for you. So, as I will tell you right now that there is for power rule it might be straightforward, but for product rule, quotient rule, chain rule, and implicit differentiation, there might be a little bit more complexity to that. Especially the examples that are provided, you need to know a little bit more about it. But let's just go to the definitions mainly. The only example thing I'll give right now is the power rule. So power rule. Basically, you're told x to the power n, and its derivative will be n times x to the power n minus 1. It's a simple formula. So if I told you x to the power fifth, what is n? N is 5. So we drop the 5, multiply it, and then 5 minus 1 in the exponent. So 5 times x to the fourth. Okay, so I think that is a little bit straightforward. It's just a little bit sim basic math if you remember the formula. Even with that x cube, I know we have used the algebraic method. As I said, the x cube derivative is 3x squared. Let's try it out. N would be 3. So 3 times x to the power 3 minus 1, which is 2. So 3x squared. So that justifies what we use for the definition compared to the power rule. It matches up. We have proved what I proved to you is basically the calculus version of finding derivative, with also proving it algebraically how to find the derivative. So interesting part about it. But now, as you're gonna see right here for the next few slides, I'm putting definitions. As I said, there's little bit more complication. Otherwise, I think the only example I'll give you right now is the implicit differentiation. So power rule, then product rule. So product rule, basically this, what is product? Product, when I told you that I told tell you write one thing times another thing, that's product. Multiplication, we are told f of x and g of x is multiplied to each other. The derivative we get is f prime of x times g of x plus f of x times g prime of x. I know this is first time I'm talking about prime. What is prime? So basically, if I told you with f of x, right, that's, you'll tell me, okay, it's a function, a normal function, called f of x. But if I told you f prime of x, now I have taken one derivative of it. F prime prime of x, that's second derivative of f function. F prime prime prime, that's third derivative, so on. F prime 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 prime, that's fourth derivative, so on. Keep on adding the primes, that's the next derivative that you're going to talk about. So right here, the first f of x in the derivative is prime, first derivative, but times the normal g of x plus the normal f of x times g prime, or the first derivative of g of x. Okay, similar to quotient rule. Quotient, you can maybe familiarize with how I said multiplication. This is something with division. Okay, so given in the format that it's not multiplication but it's a division, like a rational function, the derivative would be similar thing in the numerator, but instead of plus we have minus for this, and then at the bottom we have the normal g of x square. Okay, the chain rule, um it is basically chain rule. Think, this is like, let's think of programming for a moment. What is chain rule? Chain rule is basically, let's say we're talking about programming is that, like, we, maybe you guys have put if statements into each other. Like if you have done Python before, you can put if statements to each other. Or if maybe if you guys have done Scratch programming, you put many of the if statement blocks inside of each other and so on. Basically that's how it works. Even with, if we think about the word chain, right, we have so many of those metal things, right? You see chains in the movie, so many of those metal things, it's so connected, sort of, okay, inside here, now inside there, and so on. So that's basically the chain rule. Now, um so this is basically, as I said, g of x is inside f of x, like a nested if statement in Scratch programming or Python programming. So now the derivative, basically, we keep the g of x normal, but we release then a derivative of f of x with the normal g of x inside, and then we kick out um g prime of x. So think about, like, with the if statements in programming, if it's like, okay, we are getting certain outcomes, okay, there and there. If you have nested if statements, anything could happen in with different inputs. You can think of it like that. Or maybe, if, let's say, you are playing about with explosive and stuff, right, things can come into pieces and stuff. So like that, it's like the pieces over here. So the charcoal of the thing or the fire can be the primes or the derivatives happening over here. So now, as I said, so basically these, the chain rule, quotient rule, product rule, and power rule, these are more like you need to understand, memorize the uh understand the like you need to remember from head how is these derivative formulas are. Even for the algebraic methods you need to remember. So um now implicit differentiation, basically it's maybe you are given in a situation where it is not the dependent variable is equal to it's not a dependent equal to independent, right? You might have mixture of dependent on independent on one side and both sides and so on. So basically if we take derivative in respect of the independent variable, that is for the dependent variable, we get the dependent variable in respect of independent variable. I know that's a little bit big words, but I have an example here. So if we said x is the independent variable and y is dependent variable, sounds pretty familiar to us. So d over dx, that is sort of the notation. Now this is first time in introducing you to this notation. So d over dx, right? Forget about the definitions, but if I told you using the calculus part of derivative, what is the like what does it look like, what's the function, right? Instead of me just saying the derivative of in plain words, what's the symbol? You say d over dx. Okay, and you can, this is for any variable. I can say d over dp or d over da, d over dp, right? That's just basically saying derivative in respect of x, derivative in respect of p, derivative in respect of a, derivative in respect of b. So um that's basically what's going on. So given for this situation, getting back on track with the example, let's say x is our independent, dependent is y. So derivative in respect of x of y will give us dy dx. So derivative in respect of y in respect of x. So that's basically what's going on. So let's look at an example. This is a situation where there's a little bit of a mixture of x and y everywhere. So of course, first line, we have the function or the equation. We take derivative in respect of x. Similar thing, we are gonna follow what I had said in the example. So um, right here, we have a product rule um, that's happening right here. So this is also, as I said, as a there is also similar thing of a chain rule happening right here. So I think in this part you can recognize the product rule and then the chain rule of the release of a dy dx, then derivative of minus 8x, anything if there's a degree of 1, if there's a degree of 1, then anything with that the derivative is always to the constant, and then every derivative of a constant is equal to 0. So um it becomes minus 8, and then derivative in respect of x of 20x squared, that's power rule, n is 2, so 2 times 20 is 40. 40 times x to the power 2 minus 1 is x, so 40x we have there. Now what I'm doing right here is I'm isolating, like how in maybe for algebra, as you guys remember, find what is y, right? Like that. Now I'm asking you find what's dy dx. So right here I'm isolating one side, and then I'll divide by 6xy to get purely dy dx, right? As they say, purely what is y about when we ask algebra questions. Like now I'm asking you, now what is dy dx in this situation? So the answer we get after dividing and isolating, or isolating first and then second dividing, we get dy dx is 40x minus 3y squared plus 8 over 6xy. So um this is what I was saying about, like with the product rule, quotient rule, and chain rule. Some of the more um advanced problems with those questions require you to understand special situations um, that are not easy, right? If I told you what's derivative of sine of x, you might get confused with the definition, or derivative of cosine, okay, you might get confused with the definition. So similar thing, you might have to memorize these. So sorry if this is little bit like so much complicated and stuff to memorize, but you need to adapt to it. And especially for the tangent, secant, and cosecant and cotangent, you can actually justify using why they are using like the product, or I think mainly the quotient rule. But of course you need to understand the special situations, and then keep in mind, memorize the quotient rule. So you need to keep in mind, of course, the calculus is interesting, but you need to make sure that you remember your stuff. So um derivative of in respect of x is of e to the power x is e to the power x. So this is a rule. So this is basically, it will always remain e to the power x. Okay, but let me tell you, if I told you what's the derivative e to the power 2, technically it's zero. What's the difference? Why do we get zero when we had defined an x value versus to when we keep it as x? Keep in mind, x we do not know. If we set e to the power x, we do not know it's x. E to the power 2, I can evaluate. E is 2.71. I can say 2.71 square, evaluate it. It's a constant. As I just said like a few minutes ago, the derivative of any constant is zero. So, um, so basically, that's what's happening. And then ln of x, and at e to the power x, this can be more justified with when you're looking at derivative at a specific point. This is what you like. This, like, I believe there might be videos on YouTube that might give clearer explanations, but as I said, because of the time, we need to go. But you can always look at YouTube. Like, I know there might have been a video on YouTube that defined why e to the power x will remain e to the power x. So ln of x, derivative of that is 1 over x. Then sine of x becomes cosine of x. Cosine of x becomes negative sine of x. Tangent, with more of the proving, there's a way to prove it. You get secant square of x. Cosecant is cotangent times secant, which is negative. Secant x derivative is tan of x times secant of x. Cotangent of x is negative secant square of x. Then with the arc inverse trig functions, we get the following right here, and even with this following over here, then even with derivative of a to the power x and ln l I mean log of some base a of x, we get this information. So I don't really keep. I'll put the presentation afterwards, after the class. But I'm gonna emphasize again, right? There's a lot of memorization involved, so you need to make sure that you're familiar with these, especially if you're taking a Calculus 1 course and maybe AP Calculus AB, or even especially you need to make sure that you remember these when you take AP Calculus BC or Calculus 2 or Calculus 3 and so on. So now, now we can get into examples of the product rule, quotient rule, and chain rule. Now I'm telling you what is 8x cubed times sine of x. What is h prime of x? Reminder, what does h prime of x mean again? It means first derivative of the h of x function. So let's split it up. Let's make it simpler. Don't I know some of us might want to dive into the given situation, but when learning something new, you need to sometimes just break it down. So let's break it down. F of x, let's say it's the 8x cube, and g of x is sine of x. So as I said, this first line is the formula for product rule. So what is derivative of 8x cube? It's 24x cube. You can use the power rule for this. And then, as I said, one of the memorized things you need to know is sine of x derivative is cosine of x. Given with that, let's put in everything. So f prime of x times g of x is 24x squared times sine of x plus f of x times g prime of x, 8x cubed times cosine of x. And then right here, basically I've just like factored it out. Of course, if you had said this is correct, or if you had factored, then yes, that is correct. Just I'm just putting like that. But either if you had just done it before I have finished the explanation, then yeah, either of the two options is correct, however you prefer. Of course, follow the format whenever you're on the exam for college or um, the college board exam. Make sure you follow the format accordingly. Now, quotient rule. If I told you 3x to the fourth and is over ln of x, what is h prime of x? Okay. So basically, let's split up again. What's the f of x? 3x to the fourth. What is g of x? ln of x. So f prime of x, that would be 12x cubed. You can prove that using the power rule. what is derivative of ln of x? That's another thing you need to memorize. So that is 1 over x. So now let's place it in. F prime times normal g is 12x cube times ln of x minus f normal times g prime 3x to the fourth over times 1 over x over normal g square, which is ln of x square. Okay, so now right here, I just simplified it further and further and so on. That's why you see two fractions, because ln of x over here, so we cancel out one of the ln of x. We had this 1 over x, so that's why we are seeing x cube instead of 4, and we still see the ln square. So this is a way to, would be the final answer. Now, chain rule. Chain rule, tangent of x, tan of 4x to the power 8, that's h of x. What's h prime of it? So break it down again. What's, instead of what is, like right here, what is the first and second function for product, or what's the top and bottom function for the quotient, the chain rule now, it's about what is outside, what is inside. So what's outside, for f of x, tangent of x. What's inside, g of x is 4x to the power 8. So this formula we have, okay, tangent of x derivative is secant square of x, and 4x to the power 8, our rule tells us is 32x to the power 7. So using this formula, right, we keep g of x normal, so we drop it inside for x to the power 8. But the derivative of tangent of x overall is secant square of x. So secant square of this times we throw g x outside with a derivative or prime on it, which gives us the 32 x to the power 7. This is basically the final answer. Okay. Now we are gonna talk about derivatives of inverse functions, but just now I'm gonna take a minute right now. Any questions do we have? You can say yes, I understand, or yes. If you genuinely have a question, you can put it in right now. Do we have any questions? Okay. I okay. Now let's move on. So derivatives of inverse functions. This is also a little bit more complicated thing, similar to with the IVT I told you for limits. This is a little bit more practice you need to do. So let's say f of x is normal function and g of x is inverse functions. Remember we had learned in our first lecture that inverse functions are basically the domain and range are like swapped between the normal function and inverse function. So basically, if we say g of x is the inverse function for f of x, and we take derivative of the inverse function, the formula, right? Keep in mind, I keep saying formula after formula and so on. So now with g prime of x, we need to have 1 over f prime, the normal function of the inverse function regular g of x. So that's basically what's happening. So let's maybe go through like a short demo with this, right? It's across part 2. So let's say I want to tell you find the derivative, the inverse function at 4. The derivative of the inverse function is 4. So we are only given with this and maybe this. So of course, first thing you know, with inverse functions, you need to swap the x and y around and you solve it. So to help go faster, since that topic is a little bit of a review, this is our inverse function. Now, um, part of the formula itself is to find what's f prime. So f prime, the 2 is a constant that goes away. Power rule for x cube is 3x squared. Okay, remember we need to use this formula. So first step, we need to know the inverse function g of 4. um so that will be put inside. We got cube root of 6. Then we are gonna, since that is a nested function, writing, remember, if functions and Scratch programming and Python programming, if we were to nest everything together. So we put that in there and we simplify. So that is 3 times the cube root of 36. If we had said cube, then yes, that it would be, we would simplify this um, to where it's 6 times 3, but we're not at that point. So now just putting it everything together, g prime of 4, we have this, then we put in this and we get here. I know maybe this is a little bit confusing part. Here I just rationalize. This rationalize is just um uh, rationalize is something that you guys should remember from algebra, but just reminder if you have forgotten, because of course we have not discussed it in lecture 1. Basically you are saying that the denominator we should avoid having a radical. But why? In general, right, if I told you what is 1 divided by 2, that you can say, yeah, of course it's 0.5, but 1 divided by square root of 3, of course you cannot tell me it's like, oh, it's difficult and stuff. So we rationalize by saying square root 3 on on both sides. So like here we are gonna say the cube root of 6 on the top and bottom, so that at least we have 3 times 6 at the bottom giving us 18, and we have 1 times the cube root of 6. So either if you had told me, oh, this is the answer, or this is the answer, it's correct, but just I was taking this extra step of rationalizing. Okay, now this is something that is similar to the intermediate, the IVT, um, but the IVT, you can think of it as similar to MVT, um, but it's MVT is more specific for derivatives, compared to just limits in the IVT. So derivatives is basically saying that if we were to compare an average rate of change versus the instant rate of change, which is aka the derivative, there should be at least one C value indicating that we took the instantaneous rate of change over there, and it is equivalent to the value of average rate of change A, comma B. So it should be continuous. For it should be for different, similar to how we say continuous. Continuous, there's now something called differentiable. Continuous is same thing, but instead of smooth path, differentiable is saying, can we take derivative, yes or no? So basically the closed interval corresponds to continuous of a comma b, and open interval corresponds to differentiability, and c is that one value. So for example, let's say I told you this, f of x is equal to x squared. So um right here, if I told you this question, that closed interval of -3 comma 3, if that's continuous, and open interval differentiable, use mean value theorem to find c in the open interval. Basically, I know I have chosen a little bit of the easier route here, but basically if you take instantaneous rate of change at 0 here for x square, you get 0. It looks like a horizontal line. So basically I can take any 2 points that make a horizontal average rate of change, and that is basically what I'm doing. So um so so for example, I have taken the derivative, looked at the possible location, and look for 2 points that give the average rate of change. So as I said, you can use negative point two, negative 2.99 to 2.99, or one, negative 1 and 1, and so on, anything in this interval, and it follows the mean value theorem. So does anyone have any questions right now for this? Okay. I think no one is having questions, so I'll continue on. And guys, I'm open for you guys to ask questions in the text box. I will try to get back to it when I look back at Discord. But okay, there's two concepts: related rates and optimization. They're a little bit similar, I would say. Related rates are easier than optimization. So related rates, basically it's looking at the connection with multiple sets of informations that are hidden as variables, and it's connecting it to derivatives. So let's look at an example. So if I told you water is being poured into a cylindrical tank at a rate of 8 centimeters cube per second, the radius of the tank is 2 centimeters, how fast is the water level rising? So adjusting to the situation we are given with a cylindrical tank. So of course we have this, but we need to know how fast are we changing over time. Keep in mind, I just said how fast are we changing. That means derivatives. So right here, for this particular situation, you can either take the derivative instantly, but I would say this situation it's easier to take the plug in the values first and then find the derivative. So right here I placed in the 2 centimeters radius where we got 4 pi h. Now how fast is it rising? That corresponds to height, like it's asking like rising. If you talk about an elevator, how fast are we rising to the top floor? So similar to that, we take derivative in respect of time and we get dv over dt, we get 4 pi times dh over dt. Now we are given with what is the dv over dt, which is 8 centimeters. We plug in the value, divide by 4 pi, and we can simplify to where we have 2 over pi dh over dt. If you want to give decimal, then it's 0.637. That is DHDT, and I also specified the units, which I believe I do not know how is it for college, but for like something like AP Calc AB or BC exam, units are important. So that's why last lecture I was emphasizing about the units um, for the practice problems. Now optimization, which is a little bit harder, it's um uh, basically looking at how can we get the highest and lowest possible values. So think of it like, for example, business, right? How can we get the highest values? What makes us get lowest profit and so on? That's like optimization. So right here, an example, if let's say you had 100 meters of fencing and want to build a rectangular enclosure, what dimensions give the largest possible area? So as I said, this is one of the more hard topics that needs practice. So um yeah, so that's basically yeah, you need to have some practice for it. So let's say we are talking about length is x and width is y. We are looking at perimeter. I know we are talking about area, but just trust the process for this. So perimeter is 2x plus 2y is 100, and then um if you do the calculations right here where you solve for width, you get 50 minus x. Now we know area is the length times width. So now we can substitute that into here and then find the derivative and find the derivative and then solve for 0, where in this situation gives us x is equal to 25, and then replug it back inside to here. Um, so and then we see we have length and width as 25 units or meters. And then reason why you see I have taken second derivative. So basically, we in the next few slides we'll be talking about increasing or decreasing and concavity. So basically, in general, if I just told you just generally, no context, the normal function first derivative that talks about increasing and decreasing. The second derivative talks about concavity. So concavity right here, since we found negative, that means we like we have reached the maximum point. So therefore, gonna be this is the finalized measurements. So 25 times 25 gives us 625 meters squared, and that is the maximum area that we're looking at. Now, as I said, we are going to talk about increasing or decreasing. So basically, it's looking at is a given function going positively upwards or is it going negatively downwards? So basically, right here, we it's first derivative of the normal function, and if the first derivatives justifies we have a positive value at a given rate of change, that means the normal function is increasing. If it's a negative value in the first prime or first derivative, we have a negative slope, or the function is decreasing, the normal function. So example of it is I ask you what are the intervals for increasing and decreasing for x square. So we can always find the first derivative and put in 2x. Um, so uh, So right here we are, if we were to look at here that this is supposed to be, I believe, plus. Um, yeah, this is supposed to be plus. So if you see right here that the derivative is 2x, um, so we put in values. So 0 is 2x, and 0 is 2x, and 1, oh, sorry, 0 will give us 0, 1 will give us 2, negative 1 will give us negative 2. So these are the intervals I have said. I know this should be like maybe a closed interval, but because of 0 and negative 0 are equal to each other, that's why I did it. But forgetting about 0, by just visualizing this, how can we justify this decreasing and increasing? Let's look at the graph. If we were to draw many tangent lines, right? If you think about it, you learn from geometry secant lines and tangent lines. So secant lines are hitting figures that twice. That is average rate of change. But tangent lines are instantaneous rate of change. So, um, the if we were to look from the left side, instant draw tangent lines, draw tangent lines, draw tangent lines. From the left, we are decreasing. Draw tangent line, draw tangent lines. Here on the right side, we get increasing or positive slopes. Now, um, we have concavity. Concavity basically is just seeing that about how it curves. It's in the name. So con, C, curve, cavity. That can help you understand about curves. So there's a second derivative, and positive um, value in it means normal function has concavity up, and negative gives concavity down. So that's when in the optimization problem, that means we had like a maximum or concavity down, right? Meaning that there could be a maximum. So given with this example, we are going to use x squared again. If we take second derivative, at the same time, we get 2 only. So showing that 2 is positive, it's only occurring right here. There's a concave up. So that give because of this 2, any value place, it's 2, positive 2. That is basically what's happening over here. So um here we are. Just wait, guys, just give me 1 minute, I'll be right back. Okay, I'm back. So now we are gonna talk about something called linear approximation using derivatives. So there's as I said, relevant to tangent lines being derivatives. If we wanted to know for more complex situations, maybe sine of x, e to the power x, maybe cube roots, and so on, more complex situations, we can find the derivative at the instant point to find what's the normal, the value for the normal function as an approximate is as something to approximate. So basically, the formula, you can also call this linearization. Formula is L of x is normal f of a plus f prime of a times x minus a. But does this look familiar to you? This is actually how does this actually come from? This come from point slope equation. So as you know, y minus y1 is m times x minus x1. So basically, y1 is basically an outcome of a given x. So that is like you can say normal f of a. So f of a, we just moved it to the other side to where it's positive now. And keep in mind, m is slope. What is derivative? Instantaneous rate of slope. And we're trying to look at estimation over here, the instantaneous rate of change that is going over here. So now, and then the x minus x1, I believe, is explanatory. It's like self-explanatory. It's just the a value. So let's look at an example. I told you a cube of x, a cube root of x. So, and we wanted to know what's the value of cube root of 8.5. So we put it to here where we find the derivative first, or our reference point, our closest reference points would be 8 comma 2, right? We can put in 8 and we get 2. So we need to put in 8.5 to give us some approximation. So its slope, we need to find the derivative at the specific point. So just to simplify it, we have 1 over 12 as the slope, and then we put it into the equation. Now, given that we have the equation, we put 8.5 inside, and it gives us the approximation of 2.0417. So that's basically how we tackle with linear approximation. Now, we have L'Hopital's rule. And don't worry, guys, we're getting this is the last topic, and we'll go over connection with physics. Then I'll dismiss you guys, and the practice problems are already inside of the presentation. The L'Hopital's rule, basically, this is connecting with limits and derivatives. Basically, for a limit, if let's say we are given with a rational function, but our outcome is 0 over 0 or infinity over infinity, then how does that make sense? Basically, we need to eliminate this. We need to look at finding the derivative f prime by itself and g prime by itself, and then take limit again. If it looks like we got 0 is 0 or infinity over infinity, then we do L'Hopital's rule again. So example of such. So let's say I told you e to the power x minus 1 over x. Find x is equal to 0 in terms of limits. We plug in the value. Anything to the power 0 is 1. So 1 minus 1 is 0 over 0. Well, we cannot have 0 over 0. So identify what's f of x and g of x, take their derivatives individually. So negative 1 is constant, so go by for it. Then e to the power x will stay the same. G prime of x, anything that is just x to the power 1 will become the constant. So 1. Now let's try again. So e to the power x over 1. So e to the power 0 over 1. E to the power 0, anything to the power 0 is going to be 1. So 1 divided by 1 is 1. So our response for this is 1, and that's we don't need to do it again because we did not get 0, 0, infinity or infinity again. Now the final two slides. How does limits and derivatives come into play for physics? So limits, I wouldn't say there's not a lot of connection to physics directly, but as I said, with understanding how derivative works, and next lesson we'll look into integrals, understanding that will set up foundation of understanding how to do those concepts when you do physics. But to say something directly, no, like there's nothing much you can see. um, but derivatives, or it can be used for many things, to specify many things. So I had said before, position to velocity to acceleration. So position prime, first derivative is velocity, or prime prime is acceleration. So second derivative, or derivative of velocity is acceleration. Rate, the derivative for flow of change is current, of charge, I mean, is current in circuits. For power, energy transfer, angular velocity for angle, for the given angle. So think of it like we have position and distance versus with velocity. This is more of angular um, motion, and then wave motion is based on displacement. So now this is practice questions, but since we have met our time, um, I will put the presentation inside the area, and you guys can look at it at your own, and if you have any questions you can ask me or Alpha Tau about it. But I would like to say thank you for everyone who stayed for the session. Do we have any final questions before we end off this lecture? Just reminder for anyone who's asking, yes, the presentation will be placed shortly after this. So do we have any other final questions for the lecture? You can say no questions, or I understand in the chat. Okay. So I don't think you other three or four or five don't have any questions. So if there's no other questions, we can say that this is end of lecture two. Congratulations on finishing lecture two. I hope all of you have a good one.
You too. Bye.